Okay, this is the third section of the waves chapter, and what we're going to talk about today is how these waves behave. We need to talk about the medium on which it travels through, whether it's traveling through water or along a rope or a wire or a spring, and then it's not always traveling across the exact same medium. If you're talking about, think about impulses of electricity traveling through a wire. It's not always traveling through the same thickness of wire or not. The air may be heavier in some places as it is in others. When we're talking about radio waves, and that's why we worry about weather. If you're far out there and you're tuning to a certain frequency, but the air is more dense because of some sort of moisture or something, or there are disturbances in the air. You're not going to get that radio station just because it can't travel that much distance. You lose some of the wave. The wave is reflected somehow or deflected somehow. There are a lot of things that can occur to stop a wave, and we need to talk about those boundaries. A boundary is just some sort of change. They show two different springs in the text, where one spring is larger than another spring, and so the big spring has a wave going across it, and it reaches the boundary where the two springs are connected, and part of that wave is reflected back once it hits that boundary. So that first wave is that incident wave. That's the wave that goes toward the boundary and hits it. And then the reflected wave obviously is the piece of that wave that gets reflected back at the origin. Okay, but the rest of the wave continues on down that other medium. And it happens quite a bit. If you talk about waves in water, as the waves come to shore, things happen. Speed happens at different speed. Those waves are not quite as tall, and they can move faster if they're shorter, right? So as they come up to shore, you got that water moving in a little bit faster. Those are all different things, and we can talk about how they get reflected and how they change direction. But I want to move on to the next part, which is superposition. Superposition is kind of a weird concept to read and understand. But the best thing about superposition is understanding that waves come in contact with each other, and how they come in contact with each other and what happens to those waves is really superposition. They can either crash together and build a bigger wave if they're traveling up together and they create something larger, or they can simply just pass through each other and continue on their paths, or they can be destructive and they can take something away from each other and reflect pieces back in other directions, or become smaller. And that's really the idea of a wave that's out there and doesn't get to go quite as far because it's come in contact with some other sort of disturbance in the air. And these are big, broad concepts. There's not a lot of calculation that happens. We want to show what happens to a wave. We definitely say, we can do some calculation with it, but not you guys so much as maybe a higher level physics class using calculus. But you can use algebra to do it, and show how some waves passed by each other and stayed the same, or how they've joined each other and their amplitude is much larger. And we'll get to that momentarily. We'll get to that in the second video I do that goes through those problems. I want you to try the problems, see if you understand the ideas first, and then I'll create another video that takes you through a couple of problems to get you to the end. So we talked about the destructive properties if two waves come in contact with each other, or you even come in contact with another boundary. Sound waves constantly are moving, right? And there's a little piece of wall right here. As I'm talking, it's bouncing off of that wall and going in all sorts of directions, but it's also continuing through that piece of wood or piece of drywall, and it's vibrating through there. So most of it is reflected back, but there is some that goes through. Remember when we dropped the bowling ball, the force of the bowling ball hitting the ground sent waves down through the floor. Now, did they continue on forever through the floor? No, obviously not. It can't continue that far through that medium. It doesn't have a chance to wiggle too much, but it did create some sort of disturbance down there, and it did send waves down that way. But most of the sound waves went out, and we heard those. So let's talk about standing waves. They show a picture, a bunch of pictures of waves, somebody just oscillating a rope, oscillating a spring, and you could see that both ends were pretty much stationary in that wave, but you could see waves, right? And you could see the outer edges of those waves, and if you kept the oscillation at the same rate, then you're going to see a wave. All right, you're going to see the outer edges of that wave and a little blur in between. But seeing the outer edges of the waves is that idea of the standing wave. You say, oh, wow, we can see that. And when you work with electronics and you see the oscillations of the waves, you'll see that outer edge highlighted. So you can find the amplitudes and the wavelengths themselves when you're working with those electronics. So standing waves, I believe you've seen. If not, it's pictured in the text itself. And really, the last thing that they talk about in this chapter is reflection in two different dimensions. Most likely, it's some sort of wave that's going in a direction and bouncing off and not coming directly back at you. I mean, we don't walk around and find perpendicular surfaces to yell into so we can hear the sound come right back, although we do that with our iPhones when we want to listen to something and we don't have our earbuds handy. We turn the iPhone on. What makes the sound louder? You put the iPhone near some sort of surface, and the sound bounces off of that and reflects out, and we hear it a little bit better because the sound's not going away from us. Now the sound's coming right back at us, and that's why we put the iPhone inside a cup or something, or right next to a wall or something, so that we can hear that sound come back at us faster instead of traveling way out there and coming back here, and we lose some of it while it goes away. The next thing I want to discuss are basically showing boundaries and having waves come off of it. Now, I don't want to talk too much about the speed of waves. When we draw these figures, I'm going to just create a wall here, okay? And I'm going to have some sort of wave, and I'm going to try and keep these lines pretty consistent, but as I get to this wall, the wave's going to bend along the path of the wall as it goes, and then start to be reflected back, and it's going to turn and come back along. It's hard to draw this part in here because it's hitting the wall, but still this part of the sound is coming back here, but eventually it turns and gets reflected back out this way. You know, it's sort of like when you're shooting pool, um, and you want to hit a bank shot. You want the angle in is going to be the same as the angle out, and that's exactly what happens here. So if we have this angle here, it's really not really a good representation if I don't draw it right, right? Says the mathematician. So basically, angle in and angle out are going to be basically the same. I want this to be straight so we have the right angle. Sorry about my drawing. And if this angle is the same as this angle, then we got it right. And so that's the idea. So the sound wave is going to come bouncing back out this way, and who knows about this medium? If this is just a wall, then the amplitude of those waves is not going to change too much, and the speed is not going to change too much. So what happens if we have a wave in the ocean and we have just like the shoreline comes out this way, but this is deeper in the ocean and the waves coming in this way, and it's pretty slow, right? And then as it gets closer, it speeds up. This is it getting closer to the shoreline and speeding up so that the wavelength isn't as big, but then it starts to turn along with the shoreline. I didn't do that very well either, did I? So now the wave's headed in this direction if it's off at an angle, but not quite as wide, not quite as big. So that's sort of the idea of waves and how they react to certain things. I'm not going to force you to draw a whole lot of pictures, but I want you to be able to understand that idea that waves do turn according to their medium, and how they're allowed to speed up if it doesn't have to be as quite as big an amplitude as was down here in the deeper water. And those are really the ideas for watching this video and getting the ideas of this chapter. Today's number is 54. Okay, so if you write 54 on your page, lets me know that you watched this instead of just copying and pasting information from some unknown source. All right, so I thank you for watching, and I'll see you guys a little bit later. And if you have any questions, you just let me know.